The last part over here is talking about how to show certain properties of the binomial PMF, okay? And there are a few items that you need to know how to derive, and then there are a few others that are just optional, so I'm gonna lay them out over here. So first of all, the PMF, okay, is positive, okay? Meaning that, I should say like positive in a sense that the PMF of it is always non-negative, okay? But of course, when we say positive, or like we care about the positive ones, because let's just say, like say, if we're like the number of, the number of success, the number of 6 we can get out of 4 rows of a 6-sided fair die, right? And then, well, we define it like the success x, like random variable x can take 0, 1, 2, 3, 4, right? And then they all have actually positive probability. But then if I'm asking what is the probability of x equals to 5, well, it's always going to be 0, right? So this is what we mean by, well, the PMF is not negative, but we only really care about the positive ones because anything outside of the range that you can think of is going to be 0 anyway. And one property here that you're supposed to know how to do it, okay, is total 1, okay, meaning that the sum, okay, of all of the PMF add up together, the PK, right, add up together should be 1, okay? So my hint for you to think about all of this is the binomial theorem, okay? So one thing, I'm just gonna write it out over here. So the binomial theorem, if you remember, okay, A plus B, okay, to the power of n, okay, we know that is k equals to 0 to n, and then n choose k, right? A to the power of k, and then b to the n minus k. Okay, so we brought it back earlier as well, because this looks very much like the PK, right? So for us, PK in the binomial theorem, the binomial distribution, we know is n choose k, right? And then p to the power of k, and then 1 minus p, right, to the power of n minus k, okay? So I bring this back of the binomial theorem is because even back then in chapter 1, we saw exercises in homework. So, well, if you're trying to show certain results, maybe you just want to pick your A and B wisely, that you can get some certain really interesting results, okay? So here actually is picked for us, okay, in a sense, because P is A and then 1 minus P is B, okay? So because of that, we can actually use the result to show this total 1 result here, okay? So to do that, just recognize, okay, so we're trying to show, right, the sum of PK, okay, we expand it out over here, okay? And then from this step to this step, this is just the binomial theorem using it reversed, okay, like from here to here. Okay, we recognize A and B as P and 1 minus P, okay? So we add these 2 up together, which the P and minus P got canceled. So it's 1 to the power of n, is always gonna be 1. Okay, so this, well, mathematically shows that the sum, right, of all of this, PK equals to 1, okay? And then this is also the total 1 result, like I said, in the axiom probability as well, okay? And earlier in that example, I was saying that, well, if you add them up, it's gonna add up to 1. Here, this is very generic, okay? This is true for any binomial distribution that you're working with. So keep that in mind, okay? And a couple of other things, although not required, but I would recommend you to check out the textbook. And but the results themselves are pretty important for us anyway. Okay, so this is about the mean of the binomial random variable. Okay, if you toss a coin n times, each toss has probability p being ahead, then on average, which means that on expectation, the total number of heads equals to n times p. Okay, so putting in the mathematical notation, we're saying that if x, okay, if x follows a binomial distribution, so remember the notation here, okay, then the expectation of x is n times p, okay? Check out the textbook, page 131, okay, for the 9th edition. For the derivation, it's not required for you to know exactly how to do it, but I think going over it will help your understanding about how to work with expectation, and then in particular with this binomial distribution, okay? So keep that in mind, this result, this is gonna become handy. The second one, okay, is the variance of the binomial distribution. Again, it's not required. The textbook, page 132, gives a derivation. But for us, the result is useful. The variance of x, which when X is, again, binomial random variable with n number of trials and success probability P, is going to be n times P times 1 minus P. Okay. So one thing, even though we're not going to show the like the derivation, and then like I said, it's not required, but I do want to bring your attention back to, if you remember the expectation of the Bernoulli, okay, if it's only one trial, if you remember, we showed it, okay, success probably is P, and the variance, okay, is P times 1 minus P, okay? So pretty much what we're seeing over here is that when we're doing binomial, which is like the sequence, right? It's a sequence, series of independent Bernoulli trials, and then we're interested in the number of successes. Then the expectation earlier we showed is n times P for the binomial. Okay, the variance now is n times P times 1 minus P. It's pretty much related, like you can see, to what we have seen for the Bernoulli, which is in the box over here. Okay, so again, check out the textbook. Okay, and for those detailed derivation. Okay, and I think going over that will help your understanding overall, even though it is not required for our course. Okay. Lastly, if we have independent Bernoulli random variables, okay, just like what we're talking about, okay, and x1 through xn, okay, Bernoulli, again, they are single trial, okay, with the same probability of success P, then their sum is a binomial distribution, okay, so this, not surprisingly, right, actually it's the way that we talked about how we can think of the binomial is the sum of independent Bernoulli trials. But regardless, it's an important result to show, okay, because earlier the way that we introduced the binomial is not talking about it as the sum of Bernoulli, right? We're talking about each is a Bernoulli, and then we're thinking about the number of successes as the random variable. But it turns out that you can also rephrase it as the sum of independent Bernoulli random variables, okay? All right, to get us grounded on this, let's look at one last example. Row 4 fair 6-sided dice, okay? Let X be the number of 6 obtained, okay? So again, this is going back to our previous example, okay? So we have a binomial random variable, okay? X is binomial 4 and 1 over 6, okay? So just so you know, if you remember expectation of X for any binomial, okay, is NP, okay? Variance of it is NP 1 minus P. Okay, that's true for any binomial. Okay, so for us, we can pretty much use this result to show the mean and the variance. Okay, so the mean is n times P is 4 times 1 over 6, and the variance is n times P times 1 minus P is 5 over 9. Okay, so this is a pretty straightforward application. Okay, so to recap, okay, we introduced the binomial distribution. Okay, that's the notation. BIN stands for binomial. And then n is the number of trials, B is the success probability. Okay, you need both to determine what the binomial distribution you're talking about. The PMF, okay, is what we talked about, is highly related, again, to the binomial theorem. In fact, we use the binomial theorem to show that total 1, meaning that the sum of all of the PK add up together is 1, okay? So keep in mind how we use the binomial theorem and how they're related, okay? Lastly, the mean of the binomial distribution, which is mu, is n times P, and the variance sigma squared is n times P times 1 minus P. And then we saw a very straightforward application of this earlier of trying to figure out the mean and the variance of a particular binomial distribution, okay?